Welcome to this video on Compton scattering and photon properties. Here we're expanding our understanding of quantum phenomena from the photoelectric effect experiment and trying to develop what the beginnings of quantum mechanics developed over 100 years ago at this point. So what we're looking at here are really just the interaction between electromagnetic waves, also called light, and matter. And this is the development of an understanding of electromagnetic wave behavior. So when you get into the details and the weeds and you start to feel like you're getting lost, take a step back and just remember that the main goal here is we're trying to describe electromagnetic waves or light, and we're trying to show how those electromagnetic waves interact with matter. So that's the big picture. So we're going to start back where we did in the last videos, and that was with the photoelectric effect, because this is going to connect in theme and in some of the actual details with the Compton experiment. So the photoelectric effect, the basic idea was that if I took incident light, I'm going to symbolize that with E sub I for the energy of the incident light, and I subtracted how much energy is going to needed to break free an electron from some metal, I would have some leftover energy, and that leftover energy is going to be the kinetic energy of a particular particle. Now, to expand this very simple idea of this is how much energy I need to put in, this is how much energy is needed to just break the electron off of the metal, and how much energy is left behind, which is fairly simple if you think about it. What I'm going to say now is that this light energy over here, we're going to refer to as light energy. And Max Planck is attributed with the relationship E equals h times f, because what he showed here essentially is that frequency and energy are directly proportional. It's not the classical idea of just amplitude and representing the energy, but specifically this relationship between F and E. Of course, the E sub B, the energy to break the electron free, we called the work function, just a fancy term here that we're going to use the symbol phi to represent. And then, of course, this is the kinetic energy of the ejected photoelectrons. So this kinetic energy over here, I'm going to symbolize with a K. So if I rewrite this equation for the photoelectric effect, what I have is K is equal to HF minus phi. Now what's important here is the whole idea of the interaction between the incident light and the metal, which of course is just our traditional understanding of matter. And what Einstein then referred to this incident light, HF, as, he referred to it as photons. And I kind of like this idea that's often used to describe, they use the phrase packets of energy. So because we were struggling to put a definition on electromagnetic waves, also known as light, right? We can use those two terms interchangeably. It was very hard for us to put a label on it as maybe a whole stream of little particles, because we could see that the light was interacting with the matter. But because the light wasn't made up of particles or didn't rely on particles, it was very hard to explain. And so what came about was this term photon. So basically these little amounts of energy, and we'll get into this idea of discrete amounts of energy, little multiples of energy, these packets of energy have no mass. And this was one of the biggest issues that plagued the beginning here of this quantum phenomena that they were experiencing or that they were observing. So basically what we're saying is these little packets of energy, which are defined as the product HF, interact with the metal. If there's enough energy here to break free an electron, we'll have some leftover energy for the electron and it can move. But these packets of energy have no mass. Well, why is that a problem? Let's jump back to classical mechanics here for a second. If I have a marble, I'm going to say that's marble A, it's moving to the right with a certain velocity. if it has some specific velocity here, it's also going to have a specific momentum as it moves to the right. Now let's say that marble B is sitting here and marble B is at rest. So its velocity is 0 and therefore its momentum is 0. If we wanted to define the total amount of kinetic energy in the system before marble A collides with marble B, I'd say that the total kinetic energy of the system is really just attributed here to marble A in this form. Now, after they collide, there's a bunch of different possibilities. We could see what we refer to on the spectrum as a perfectly elastic collision, or a perfectly inelastic collision, or somewhere in between. Now we know that the major difference between these was that an inelastic collision, the total kinetic energy before the interaction happened did not equal the total kinetic energy after, sorry, I should put this as final rather, after the collision. Whereas an elastic collision would say that all of the kinetic energy total initially, I should put the 0 on that side, initially was equal to all of the total kinetic energy after the collision happened. So it just depended on a variety of different factors that you could have. So let's say if marble A hits marble B, and marble B has a temperature change, so an internal energy change, then A will not transfer all of its kinetic energy to B. Some of that energy is going to go into the form of a change in internal energy. So if we look at this idea here as a photon interacting with the matter, we can see that the photon had some energy. It hit the metal, but the metal took some of that energy just to break the electron free. There was a change in internal energy of sorts, and the result, the leftover amount, was the kinetic energy, which would be the difference between these two. The issue arises in the fact that if we are trying to relate this to the quantum experiment, marble A is really representing the photon or a photon of light, or a photon of electromagnetic waves. And we know that photons have a mass of 0. However, there is an interaction. Well, there was a very important equation that you've all seen before, which is E equals mc squared. We're going to get to that one later on. But a major idea here is that the relativistic energy of the photon, and we'll talk about why it's called relativistic energy later on, relativistic energy in general is equal to mass times the speed of light squared plus the momentum times the speed of light squared. So there were these two terms that contributed to the total energy of some mass energy experiment or a mass energy interaction. So in other words, we're trying to find a way to describe an interaction not only through mass, but also through energy, and say that those things are interchangeable in some form, but they're also distinct in some form. Well, if the photon has no mass, this term is 0, and what I'm left with essentially is E equals P times C. So what this is relating is the energy of the photon, so we could call that the photon energy, and this is the photon momentum, and then this is the speed of the electromagnetic waves, or known as the speed of light. So this was able to, was predicted to be the energy and the momentum of the photon. Well, of course, we know that the energy of the photon could also be shown as h times f, and now we can see it's equal to p times c. So we can actually relate the frequency or the wavelength to the momentum of the particular photon, which became very, very important. So, to Compton, where the heck does Compton scattering fit into this big picture of other information? What's going to come into play here, and remember what I said before was the big picture is we're trying to explain how electromagnetic waves, aka light, interacts with matter. So I'm going to show you a little animation of the photoelectric effect on the atomic level. So let me pull that up here. And if you see, that's the incoming photon. It hits, it is absorbed, and a photoelectron was ejected. Let's see that one more time. Incoming photon, it's absorbed, and that electron has gained that kinetic energy. Well, the Compton scattering experiment occurred in the following way. This is just a diagram of the experiment, a very basic diagram. We have an X-ray tube, so basically we're producing these high energy photons over here. The high energy photons are interacting with the graphite target over here, so some sort of matter. Okay, so let's put some terms over here. We have photon, a high energy photon coming out here, interacting with this, which is matter, and the result was something very interesting. Here's another schematic diagram of the experiment as sort of as a whole, looking at it as a whole. This is the wavelength of the incoming photon. So we can relate that as energy. So we're going to say energy equals H times F. We know that C equals F times lambda. So energy must equal HC over lambda. Okay, now the reason I'm doing that is I'm trying to show here this is the photon wavelength. And when it collides with the graphite target over here, we see the ejection of an electron. And we also see, and this is a really important part, not only that ejection of the electron, which is what we saw with the photoelectric effect, we see this emitted wave that has a different wavelength. So I'm going to write the wavelength equation, energy equation here, E equals HC over lambda. If the wavelength increased, then that means that this photon has a lower energy compared to what it had originally. And it turned out that there was a relationship between the angle at which the photon scattered once it interacted with the graphite target. So if we look over here at this little graph, we see here that we have energy in kiloelectron volts, and we have the angle over here of the experiment. So this is the angle that you could adjust and hit this with as it went through. And we see a really nice relationship between the energy of the electron and the energy of the photon. Where the electron gained energy, the photon had lost some energy initially in the experiment, which really does actually align with this whole idea over here. And it's providing us with more confirmation that the photon does have momentum, and the photon can interact with the particle, and it's not some weird independent overlapping of motion. It's actually interacting. We know that because its wavelength increased. It lost energy during the interaction, which is what the most important part is. Now, this isn't very important to us for this video here, but I'm going to show that we do have a relationship that we could explain between the angle and the wavelength by showing this. The new wavelength that's scattered, that is emitted as it comes out of the graphite here, is minus the initial wavelength, so that's a wavelength difference, is equal to h over m of an electron times c. Now that's just the momentum of the electron, its mass times the speed, times 1 minus the cosine of this angle. So this is just relating how much this deflects and how much energy it has can be measured by knowing the angle of the experiment. So let's take a look here at a little animation for this scenario. So I'm going to pull that up over here, and this is known as the Compton Scattering Effect. Okay, now we'll play it again for you here. So let me reverse this. So we see here an incoming photon. It hits, and we have an emitted photon and an emitted electron. And if you take a look at the color of that, so here I'll play it one more time for you. If we take a look at the color of that, well, it's not going to work, but if we take a look at the colors of these, we had this incoming, they showed it as a yellow photon, and when it ejected, it was red. Well, we know that the energy of the yellow photon is related to its frequency, and yellow light has a higher frequency than the red light does, or a shorter wavelength than the red light does. So this is supporting the idea that the Compton experiment supports the idea that light interacts with matter, and light has some matter-like properties or matter-like behaviors, namely momentum. And when there's an interaction, in this case, it's some sort of inelastic interaction because we have a change in some energy that's not mechanical, that's not kinetic, that there is the result that we would expect where the energy is being traded off between the photon and the electron. So I know this video is a little bit long, but it's very important to get your mind wrapped around the basic ideas from the beginning. And what we can do then is take a look at some of the other experiments. So in the next video, we're going to take a look at the de Broglie hypothesis and how that hypothesis really blew open the doors of quantum mechanics.